Okay, so we're going to be doing lead code 34. Find the first and last position of an element in a sorted array. So this can be a bit verbose, but it's it's a very nice question, very good exercise in using binary search to exclude portions of a sorted array that you do not want. So binary search is basically an exclusion algorithm, right? So anyways, let's read it and we figure out what they're trying to say. So you're given an array of integers called nums sorted in non-decreasing order, in other words, ascending. Find the starting and ending position of a given target value. If target is not found in the array, return -1, -1. You must write an algorithm with O log n runtime complexity. So this is an example. We have nums, which is 5, 7, 7, 8, 8, 10. And the target is 8. So we find this. This is at index 3, which is 0, 1, 2, 3. And this is at index 4, which is, this is the leftmost, and this is the rightmost, right? As you can see, the output is an array of 3 and 4. Here we have a target of 6. This is 5, 7, 7, 8, 8, 10. And 6 is nowhere to be found. So this is -1, -1. And then we have nums is equal to an empty array. And the target is 0. So you simply return -1, -1. So if you know how to do binary search to find a target, then you know how to find this, because for this, we're going to use two binary searches. The first one will find the leftmost, and then the second one will find the rightmost. So the good thing about doing this is that you'll learn how to figure out both the leftmost and the rightmost, because most likely what you'll have known is how to find the leftmost, right? So let's first do an n-time solution, right? So the n-time solution is you simply iterate through from left to right. Actually, we don't need to code it up. You simply iterate from left to right, and then if you find the first occurrence of the target, you append its value, and then if the next one is also target, you append its index to the output array, right? But if the second occurrence does not equal to, but if the second occurrence is not the target, the second occurrence after the 8 is not the target, then you just return -1, -1, right? But now let's do the log n example, right? So log n, O log n solution using two binary searches. So the first binary search is to find the leftmost index of the target value in the array. So how do we do it? We have two pointers. I is equal to 0, j is equal to length of nums -1. While I is less than or equal to j, we calculate, we get our mid, which will be mid is equal to I plus, in brackets, j minus I divided by 2. This can be written as I plus j divided by 2 as well. I plus j divided by 2. So now we're trying to exclude these and have our I end up at this position. after we exhaust the binary search. So what we need to check is if nums at mid is less than the target, then I is equal to mid plus 1, right? We're trying to exclude any number less than the target, right? So let me show you what this is on a diagram. Right, we have 5, 7, 7, 8, 8, and what was the other one? 10. Right? 0, 1, 2, 3, 4, 5, 6. This first binary search is we're trying to get the index at this position, right? So we're trying to exclude all these. So what is the equation for excluding all these? It is nums at mid, and remember our target is 8, right? So nums at mid less than 8. If it's less than 8, we increment our I, right? Our I starts from here. And the reason we do this is we want, after the binary search is done, we want our I, because the condition for terminating the binary search is I less than or equal to j, right? So once it terminates, I will be past j. And we want, once the binary search ends, it ends up at this position. So we exclude all numbers that are less than 8, right? So that's the idea behind it. Else, that means nums at mid is greater than or equal to target. So j is equal to mid minus 1. So the other thing is, when we go back to our diagram here, conversely, another way to represent this would be to say we have 5, 7, 7, 8, 8, and 10. Another way to exclude would be to consider where our j pointer is coming from. And we say we want to exclude all those that are greater than or equal to 8. So that means excluding this portion, right? And if you look into the code, that's what this else condition is. So that means once this algorithm terminates, once the exhaustive search is done, our j, let me erase this. Our j will exclude all those and end up here, right? So this whole condition means our I will end up at this position while excluding this, and our j will end up at this position while excluding this. So in order to find this target after this code is done, in order to find the position of, if you look in the diagram of this, right, we either return I or we return j plus 1, right? So for me, I've just chosen to use I, right? So we come back down here into our code. So our I should be at the leftmost index of target, and j plus 1 should be the leftmost index of the target, right? But before moving on, we need to check that it did indeed exist in the array. And how do we check for this? If we check for this, we check whether it existed in the array by doing this. If the target did not exist in the array, our I would have either gone off, right? It would have been larger than the length of the array, larger or equal to the length of the array because it's a zero-based index, right? Or it would have been at a position in the array where nums at I, say it's here, nums at I does not equal to 10. Does not equal to 8, right? So there are two conditions for the failure to find this, the leftmost index. And obviously, if you fail to find the leftmost index, then that means that, that obviously means that there's no rightmost index, right? So before moving on, we need to check that it did indeed exist in the array. So if I is greater than or equal to length of nums, this means that it fell off, right? So if I went outside the array, or nums at I is not equal to the target. So if I is greater than or equal to length of nums, or nums at I does not equal to target, then it means leftmost index doesn't exist for target. As such, rightmost index doesn't exist either. So we simply return -1, -1, right? If we reach here, we know that the leftmost index existed, so we set our leftmost index either to I or j plus 1, right? So we say leftmost index is equal to, let's say, I. All right. So now we start looking for the rightmost index. Right? So we have to set our I back to 0 and our j to length of nums minus 1. So this is our second binary search. Right? So for the second binary search, let's write it up here. While I is less than or equal to j, we calculate our mid is equal to I plus, in brackets, j minus I divided by 2. So what's our condition to find the rightmost index? So if we remember the condition to find we have 5, 7, 7, 8, 8, 10. The condition to find the leftmost index was either to focus on the I, which would be nums at mid less than target, right? But now, in order to find the rightmost index, right? This one. we can decide to exclude all these with the I, right? So that means once our search is done, our I will be at this position, right? Because what we're doing is we're saying nums at mid is less than or equal to target, which is this portion, right? So once we exhaust our binary search, our I will be at this position. And our J will be at this position. Why? Because the loop terminates when I is greater than J, right? So to find the rightmost index, either we return I minus 1 or we return J, right? So let's write it here. So if nums at mid is less than or equal to target, we're excluding all those, including the target. So our I will be just one position, right? After binary search, I will be one position after rightmost index, right? Because we've excluded all, including the target. So I is equal to mid plus 1. Else nums at mid is greater than target. So that means we want to, so for J, when we come back to this diagram, for J, we're excluding all that are larger than target, right? And it's this. So think of binary search, whatever condition you put in the binary search for comparison is the exclusion zone, right? So J is equal to mid minus 1. So after all this, the rightmost index is going to be at J or I minus 1, right? So we simply return our leftmost index and I minus 1 or J, right? So to find the rightmost index, our J, we return J or I minus 1. To find the leftmost index, we return I or J minus 1. So let's run this code. J is equal to, oh, I made a mistake here. Voila. So this works, right? And this is a log n solution to this problem, right? So thank you, and this was the solution to LeetCode 34. This is a binary search variant question. Thank you, and bye.